Okay, RSA. Revest, Shamir, Alderman. Have you guys got to that part of the book yet? Okay, it's pretty interesting. Okay, 1978, based on factoring large numbers 200 digits apart. The examples you're going to work with are much smaller, okay? Best factoring algorithms are exponential, okay? There's no known weaknesses, but there is a weakness. One of my students brought it up because it was actually, I forget what it was called, there was some encrypted USB drive that, it was basically the hardware was the flaw, it wasn't the algorithm. It was a flaw in the hardware that allowed it to get exploited. But the algorithm has no known weaknesses at this time. It's still being used today. Okay, here's how it works. You choose a large n, which is equal to p times q, which are both prime numbers. I will provide you with p and q. So I'm going to provide you with p and q. You can multiply them to get n. So if p was 3 and q was 5, n would be 15. So far, so good. Everybody go with that? So n is p times q. Easy enough. Now we need to choose E relatively prime to the totient of n. Okay. The totient of n is p minus 1 times q minus 1. So instead of 3 times 5, it's now 2 times 4. So the totient of n would be 8. So the totient of n is p minus 1 times q minus 1. Still easy. You all agree? Not hard. Okay. Now D, I'm going to show you how to get D, and I'll make more things make sense. But D is the multiplicative inverse of E mod totient of n. Show you how to do that. I'm going to show you how to do all this. Don't worry. It's so easy. You can be like, dude, this is like the easiest one known to man. It is. It's very simple.
Just a little bit of calculus.
Yeah. Nah. No calculus required. So here's how we do it. We take our plain text P, encrypt it with our encryption key N. I'm sorry. Encryption key E, then mod N. That's it. It's encrypted. So P to E mod N, and you're done. A little bit easier than the knapsack, isn't it? Or Des or anybody else. Then how do we decrypt? We take our ciphertext raised to the D mod N. We're done. That's it. It doesn't matter which key you use as long as you don't get them mixed up. So in the second example, I can encrypt with a decryption key. Doesn't matter. And then decrypt with the encryption key. It really doesn't matter as long as whichever one you say, you know, is encrypt, you just don't mix them up. Okay? Now it's talking about totient of n. This is off the internet. The totient of n is also called Euler's totient function, defined as the number of positive integers less than or equal to n that are relatively prime. In other words, do not contain any factors in common with where one is counted to be relatively prime to all numbers. They're called totatives. So if there's 8 totatives for 24, that would be 1, 5, 7, basically all of them that are less than 24. So the totient of n in this case would be, totient of 24 would be 8. Do not do it this way. Okay? One of my students did that. That's why it's in red. Do not do it this way for the assignment. I just want to tell you how it was really done. But again, we're using numbers that are way too small. Remember, our numbers are supposed to be 200 digits long. I can't make you all do that. So don't do this. All right. So now let's talk about the math behind it. You do not need to memorize this. Okay, the Euler totient function, this is number of positive integers less than n that are relatively prime to n, as I just said. Okay. So for P, it would be the totient of P would be P minus 1. But basically what you want to get is on the next slide. Don't worry about the math behind here. You don't need to know it. Okay? Don't worry about it. Not important. Okay? No, you really need the next slide. I'm not going to even cover this because it's not on the test. You don't need to know it to do the assignment. This is what you need right here. Okay? Here's exactly what you're going to see. Suppose P is 3 and Q is 11. I will be giving those to you. Compute n. So n is P times Q, or 33. Everybody with me so far? Easy enough? If I give you 3 and 11, you can calculate 33. I'm assuming everybody can do that. The totient of n is p minus 1 times q minus 1. So it'll be 2 times 10, or 20. So now we know n is 33, the totient of n is 20. So far, so good? Super easy. Choose e that's relatively prime to 20. I will provide you with e. I will be giving you e. Okay? Find d such that e times d mod 20 is approximately equal to 1. The answer for that is 17 in this example. I'm going to show you how to get that in a minute. We're going to do that one here in a couple slides. Okay? I will show you how to do d in a minute. So, my public key, e, which I gave you above, is 13. Okay? My n is 33. Y'all see where n came from. So my private key, d, which I gave you just on 2 lines above, is 17. Again, my n is 33. So if my plain text 7, it's 7 to 13 mod 33, which gives you 13. Then 13 to 17 mod 33, which gives you the 7. So it brings you right back where you started. This does work both ways, unlike the knapsack. Can you do those? Okay, here's what you need to be able to do. These two right here. Y'all see these two? You need to do this one. We haven't covered a how yet, so don't freak out yet. And then giving these values here, which you already got up there, can you do this little last 2 lines? I mean, it's not hard math. P to the E mod n, C to the D mod n, done. That's it. Okay. How to calculate D. To compute the value for D, use the extended Euclidean algorithm to calculate it. And you're like, what? It's also known as modular inversion. Don't worry about this. It's even easier. It's going to look so familiar, right? Not yet. Soon. It's going to be in a couple slides. You'll see it in a second. Well, maybe 2 more. I can't remember what slide it's on.
Modular inverses earlier.
Well, no, we're getting there yet. We're not there yet.
For inverse.
Okay. Yes, kind of the same place. So, for using RSA, we need to pick prime numbers. They're normally 100 digits long each. We want to calculate n, so that would be p times q, which is 200 digits or 512 bytes or 1024 bits, recommended for security. Choose relatively large e's, prime to the totient of n. Compute d, which we're going to do, and then we know the public and private key. And once we get our e, d, and n, we can actually delete. We don't need p, q, and totient anymore. They're no longer required. All we need is e, d, and n. All right, now let's talk about congruent for a second. Use in mathematics, it says corresponding or congruous is coinciding exactly when superimposed, like triangles, or of or related to 2 numbers that have the same remainder when divided by a third number. For instance, 11 and 26 are congruent when the modulus is 5. Okay, not important, you know that. We're getting close to figuring out how to do D. You might want to move it up one of these days, but make you guessing. So here's an example. If I do P is 3, Q is 11 for the RSA crypto system, the public key coefficient is 13, compute D. So there's P, there's Q, and there's N. We already did those 3. So we already know the totient of N as well. That's 20. Nothing new there. To give you E is 13, what is D? Because E times some number, mod the totient of N will be approximately equal to 1. So 13 times something, mod 20 is approximately equal to 1. That's what we need to find out what that number is. This look familiar? That's exactly how you do it. Exactly. But for this, you use the totient of N and E. Okay? Remember before you use what? N and
W and N.
Yeah, W and N. So you use the totient of N and E. Just find the comparison. That gets 17. See that? That's why I made you do it in the other one, because I knew you need it. So this is exactly how you do it. And I actually had a guy who looked up all kinds of stuff, and he says this actually works the best every time. So, all right. So summary. We know what n is. N is p times q. Again, I'm going to give you p and q. We know what the totient of n is. That's p minus 1 times q minus 1. We need to have an e, which is less than n, but again, I'm going to give you the e. We know how to calculate d. D is the totient of n and e. Okay, it was e, wasn't it? Yeah, totient of n and e. Okay, then we know how to encrypt and know how to decrypt. That's it. That's all there is. Very simple. So could you do this right here? You can do it. That's literally the entire thing, as long as you can do that. So I told you RSA is simple. All right, that's the end of these slides.